Hey folks, how's it going? First and foremost, I'd like to kind of like apologize. I'm very sorry for not being consistent. I think I dissed you guys for the last past month. Um, I'm gonna try by all means to be as consistently and try by all means to give you the best possible content so that we can both learn together. Every week I'm gonna try by all means to give it my all. But today I want to look into this pre-training challenges in large language models. So I've created this repo. It's more like I'm open sourcing some of the challenges that you don't necessarily find in research papers that much. It's more like the bugs, the mistakes that maybe research labs did, the solutions that they tried but never worked. So you hear these kind of things more in a more like a talk. Let's say a researcher has been invited to give a talk, and there are questions, and that's where like they kind of like open up about these challenges. So I had to like kind of like do a research and try to go and find all of these pieces. We're gonna look into Bloomberg, their problem on dust divergency. We're gonna look into Hugging Face. Hugging Face, this project, which was the VL model, was not made a public. It was more like an internal node. We're gonna look also at OPT. So yeah, so this is going to be quite interesting, and we can learn together and see what are the challenges that some of the research lab face. So without wasting any time, let's get into it. So Hugging Face released a 50B language model. This model was trained on public data as well as some of the private data. So this is the data within Bloomberg. I think dating all the way back from 2007. So yeah, like I think it was a 50% their private data, which is more finance than public data was more. I think also it was 50%. I thought I should include this because as we go through these challenges that the folks faced, and you will start to think maybe the data quality is playing a huge role. So if you see these research labs, the researchers they tweak some of the hyperparameters, but and they try to follow like what some people did previously, but then they see these divergence again. So we might come back and discuss this data portion. That's why I had to include the data set that these project used. And I had to include some of the major difference that Bloomberg did not follow from the open source world. So what they did was to remove the embedding layer, and they use a different tokenizer in which their goal was to kind of like be able to tokenize multi-word as well as separate numbers into like single digits. So I just included this regex that they used, and they had this thing whereby they sorted their data chronologically, right? With the intuition that so we don't want the recent data to be overwritten by the old data. So if we sort it, right, this is also what we call curriculum learning. I think there was a paper on that. But the idea is that if you're gonna pass your older data, then you later pass your recent data, then the model will have much more understanding of the recent data. So that's the important with this chronological sort, which we'll find out later that they were not sure if this actually did help, and they saw some divergency. But anyway, this is their first training, right? Training loss diverge after 10K steps. So there was no improvement for dev loss after 20K steps. So this is the curve that they have shared, and this is the number of steps that they have shared with us. And they also observed some of the grade num spikes, which we see especially grade norm and activation norm and loss skills, these are correlated. So you will see the spikes, then you know that your loss will also diverge. We will see this is consistent across the project. Um, so I will come to these diagram as I explain some of the challenges. Okay. Anyway, like I said, solutions that did not work. So the first thing that they thought, the intuition here was that, okay, cool. If we pass the all the data and we pass the recent data, like like sorted all the way from 2007 up to until now, the model will be able to remember much more recent data, right? It will have much strong understanding of like much recent data because of that is good, right? Because when you're doing inference, your assumption is that people are going to ask the model like more recent challenges that they face. So that's why they employ this. I just linked the paper for those who are interested. This is also called curriculum learning. So what they saw is that they saw a gap between training and validation laws, as we saw here, right? And then the intuition was that because of how they split the validation as well as how they split the training data. So the validation set was made mostly of the future data, whereas the training data was made of the recent as well as the older data. So when you kind of like start, because you sorted this data chronologically, so the training data was seeing the older data, whereas validation set was seeing like a recent data. So this is just like you're trying to understand what could cause this. So it's one of the debugging of this discrepancies that they were seeing with this curve. Okay. um yeah, like I said, that I have to note this because the team mentioned that they were not unable to ascertain if this technique did have a negative impact because there were so many factors. And I want to say this before I continue, is that because of these labs, they have a specific budget, and like training LLM is very costly. So what happened is that their experiments, they kind of like experiment with one factor, like that will be expensive. So sometimes like they change a lot of things, and among those lot of things, they don't know which one actually worked. So so that's why I also had to include this note that it might it looks like some of the researchers might have thought it could have worked, but maybe it was something else. Anyway, yeah, keep calm and lower your learning rate. So as you're gonna see as we cover these other project, this is like your typical this is where you run to, right? This is where you run to. If you see divergence, you just go and lower your learning rate. So it's like lowering learning rate is what you need. But in this case, like I said, these are some of the things that they tried but did not work. To overcome the grade norm spike, the team followed the meta OPT tip. So the OPT tip was that if you rewind back prior to any gradient spikes and start training with lower rate, right, you will get like an improved model. Bloomberg tried that and they said, nope, that did not work. So, and we can see like from the spike, the orange. So you know what the learning rate does? You can see that it actually delays the spikes. So it does not necessarily eliminate them. So you can see that, okay, the blue one, there was a spike, but then the orange, it occurred later in stages. So it was quite funny to kind of like see that. But anyway, but there was some success, right? Which we're gonna cover why they got the success. So after 42 days smooth run, this is where they hit a rock. Like this is where like the validations laws start increasing, and the team started like doing certain things. And so the first thing was like, okay, learning rate, that we spoke about, they did not work. But then they shuffle the data from step 1115500, whereby they thought that okay, maybe it was because of some of the data that the model that step was encountering was probably bad. So maybe they thought shuffling will help, but that did not help. They added more Dropbox noise regularization method. That did not help. Reduce max learning rate. That did not work. Reduce weight decay. From 01 to 001. That did not work. Start run from different steps, which is also one of the advice that I think OPT team said that they did, and this actually helped them a lot, like going all the way back, rewinding all the way back. But for the Bloomberg folks, that did not work. It was like you kind of like see your loss is just going smooth for 42 days. You're happy, everything is in the just going great. And then after that, I just can't. I don't know. I hope you guys actually come up with good reasons as we're gonna cover some of the stuff that they did. But I just don't know why the loss like just didn't want to go up after that. After the folks have tried a lot of things. So now I'm covering solution that worked. So what got them to 42 days? Like what helped them to get to the smooth run? Uh, so I state here that please note that the balloon changes led to a smooth run, but the team cannot conclude which of the changes below were decisive towards a leading successful training run. Yeah, like I said that like you make these changes, say a lot of changes, then you train. So they are not sure which of these things could have worked. So they used a different floating point in the LM head. So this is the 32 instead of 16. Um, they use a gradient clip value of zero point 0.3 instead of 1.0. I think this is also what the folks at OPT did. They fully shuffle the data. So instead of like doing that chronological order sort thing, so they thought that okay, you know what, we want to stabilize the loss from the get go. So we're gonna try to shuffle the data, all of it. Like we're not gonna like sort it or do that curriculum learning that we spoke about. So so yeah, they reintroduced the layer norm at embedding layer. So this is they said that is just an additional precaution because of I forgot to say this, but what happened was that they realized that actually at the early layers, like the first layer, you see these grid norm spike, they deviate. So like the problem is at the first layers. This is where you're gonna face a lot of pains. So this is why they had to add like layer norms, as we will learn also with other research labs. This is what they tend to eat. They tend to add as many layer norms to kind of like stabilize this. But anyway, they use longer learning rate warm up period for 1.8 steps. Remove incorrect use of weight decay on layer norm multipliers. Or what did they do? They use a different seed to ensure different initialization. Use Megatron initialization scaling. Apply the query key layer scaling. Apply also a batch size warm up. So this is the things that the folks try to do, and these changes that they did and seem to have worked well, given that although I don't know why after that 42 days, like even if like they made small changes, why like they hit a rock, like they that they just couldn't improve anymore. um, some of the leanings, right? So Bloomberg, they said that okay, maybe they should have used some of the components that tend to stabilize training. So this is like into rope embedding, you normalize your query and key in the attention layers. You have your seed glue activations, like they did not talk about the RMS norm. So I just added it there, just to left a question mark because of, like I saw llama. Some of these recent models, like they use it. I mean, like, given that they had like 70 layers, I think, so it might have helped because this is what this normalization help us with. Like, it can, um, if you have a very deep network, as it was proven, this I tend to work if you have a deep network. So I think maybe it could have also worked. Um, they gave us an advice as I was listening to talk. So they say that start small, work your way up, and run ablation test on small model before scaling up. I find this to be quite important. Like, if you're gonna start big, right, as we're gonna learn with other research lab, you're gonna run into a lot of bugs, mistakes, code, and these some of these mistakes will look like pretty much silly, but trust me, they happen, and we are people because we we sometimes we don't think like there might be a bug, right? But they happen. So so it's funny that all of them, they say the same thing: start small. And it's more like a machine learning 101, because they say that if you start small, then you kind of like go up, you get to like test like your component, you get to see where the bottleneck is. So starting small is very, very important. So the bugs that they encountered was around the weight decay. So weight decay, because of it pulls weight towards zero, but then they initialize these zeros to center around one, not zero. So the punchline is that we should not apply weight decay while we initialize our weights to center around one. So that's the thing. I think they might have fixed that, but also I think after they fixed it within their vision one, then they went to vision two. Still, they find a lot of challenges. So yeah, I think these things here. So we don't know who the hero is among these guys here. But anyway, let's go to Hugging Face. So this is lost of agency learning from the Hugging Face team when they were actually training vision language model. Actually, I should say they were fine tuning it. But this was shared from a Word document report. It was not a formal report. It was more like the things that we learned for the past 3 months. So they did not share like a lot of details around like the number of params and the details about the models, the data that they use to full fine tune the VL model. So that information was not shared. So the main goal was to get across was like, well, how we kind of like fought the lost divergency thing. So the punchline was that the team essentially combined the pre-trained backbone, which was the vision encoder and the language model backbone. Then they added newly initialized blocks so between these layers. So then they were going to optimize these blocks. Then the pre-trained block backbones were the ones that were freezed. Then they were gonna train these newly added blocks. It turned out that these newly added blocks turned out to be a stability nightmare. So the team faced loss divergency when they were actually training with the mixed precision PF16. And then early stage of 2 to 3 billion scale, they saw this spike. So that's the challenge that they faced. So the main challenge was also around the activation and gradient explosion. Because of there's a high correlation between the grad norms as well as the activation with like the loss scale. So if like these explode, also you're gonna expect the loss to diverge eventually. So they tried to grill deep and try to see actually what was going on in these blocks, right? Within those blocks, they went to actually the specific modules, and they find that actually the outer projection activations within the MLP block, as well as the output, the O of the attention block, that's where the huge impact was. So the component of query key and value suffered, but that did not really suffer that significantly. But what blew my mind was to see that actually when they were doing their run with BF-16, that's where these explosions occurred, compared to doing their run with FP-16 run. And my initial thought was that, BF16 is much safe because even though you kind of like get a hit on the precision, but uh, you know how the optimizer work. Even if you initially get like even if you got like your direction wrong, eventually you're gonna like get into the right direction. So you might slow the training, that might slow training, but eventually you will get in the right path. Compared to FP16, in which you know you're gonna overflow, so that is gonna hurt you more. So it was quite interesting to see that actually FP16 did run, and we can see that even TAS also says the same thing, which he wrote this blog from, which was the Blue Megatron Deep Speed blog. He also mentioned that the FP16 was a no-no, so that's why I was surprised why in this case it's actually stabilized training. So this kind of like shows us that we have different things that we try at different labs, and we have different outcomes, and certain things that work for someone might not initially work for somebody else. So hence it is important that we add things like data set, the architecture, the things that we used, so that like when different people are trying to see what actually went wrong, they can actually try to reason much more, because I do know you guys probably want reasons also. You want to understand why these things were not stable, right? And I do also want to understand actually why things are not stable, rather than like changing parameter and trying to see what works and what does not work. I also want like some sort of like a reason why these things do not work. That's why I created this open source project whereby probably we can share openly like some of the things that we tried in different labs and they did not work. Anyway, coming to the solution that did not work. So could it be that probably the reason the team saw instabilities within their training run using the BF16, was it because of probably those big bones were trained using the FP16, then they were trying to use the BF16. So probably that's one of the reasons. Maybe not, because looking at the some of the older repos that I kind of like went through, analyzing the TF5, a lot of people had a lot of problems with the TF5, and they were getting a lot of issues. There are a lot of overflowing, right? Their loss will lead to like NAA or something like that. So we can see that someone came up with a solution here, and he was like, if like you can clip the hidden state to the maximum data type that you're currently using, that actually works fine. We can also go to the Hugging Face repo. We can see that someone also made a comment to say, essentially, if you try to scale your weights, then that can actually help you out. So that's what they did. Like some people scale the parameters of these modules within the transformer blocks, and uh, these are some of the hacks that people did at the time to kind of like work around this. And we're gonna get into like some of the modern techniques. I think some people use loss scaling to kind of like work around this overflowing problem as well. We're gonna discuss that. Anyway, what happened was we have the weight decay. So the idea with with weight decay was that okay, probably we should keep the weights. We should prevent the weight from going far from zero, so that's why they used a heavier weight decay, but still did not work. They still face the diverging problem. The second idea was probably to say maybe the placement of these newly initialized parameters, we're placing them incorrectly. How about we place them between the language model layers? But also, this did not have any problems. It did not actually help, I meant to say. You still remember when I said that when they drilled deeper to look at who the culprit was, they found out actually the outer projections and those modules like the FC2 as well as the outer projection, that's where they saw like huge spikes. So they thought maybe if they try to apply the layer norm there, maybe things will come to reasonable values, but this did not also help at all. Then we have hyperparameter tuning. They played around with these parameters and none of these works, including the Adam optimizers like beta 1, beta 2, epsilon. None of these worked, like came to kind of like improve or stabilize the training. You still remember when I said to you that data is quite important, and it's nice to see that also the folks try to think of maybe let's try to rank the data, use like the open page rank, and only get like highly ranked web pages only. Then we try to kind of like try with much more quality data. That to them like this must be a quality data because of it's highly ranked. But they said that it did not have a significant impact. So, but they have to say that maybe if they trained the bigger model, maybe this could have helped. So they were not sure. Like I said previously, that essentially most people like because of they train these at scale, so you can't test one factor. You kind of like test different factors, and sometimes you're not sure actually what worked at some point. So let's get into a solution that actually worked. So, inspired by the paper from, I think it was Google, scaling VAT to 22 billion parameters, what the team did was to apply the layer norm on the Q and the K projection. So initially they did not do this because the assumption was that the softmax essentially will bring the values to a range of 0 and 1, even if that's the case. But then they realized that actually this did not stabilize the training. They did needed to bring this layer norms. So they also tried with L2 norm, similar situation, stabilized training, but they had to say that this did not lead to like a high performance. Um, One thing that they said that unfreezing the layer norm from the frozen language backbone. Remember that we said that those backbones, pre-trained models were frozen, but they unfreezed certain modules like layer norm. They realized that this helped the diverging models to recover, but the team said that they deemed it also as unnecessary. You still remember about the root mean squared layer normalization. In this case, the team said that it tend to be beneficial, and which is what I think that I also that's why I left it here on the Bloomberg data. You know, I wish the team also tried to use that. Probably it would have helped. Um, Then they said that they had no biases in layers. So this also the team said that this actually worked fine. Keep calm and decrease your linen rate, even if though this is where we always run to. Hugging Face in this case, they also had to say that even if we decrease the linen rate, that's fine, but it's important to have bigger batches because of now this will allow you to have bigger linen rate, which will and then allow you to have faster loss divergency, not divergency, loss decreases. Yeah, so that's what they it's more like a lesson learned thing, that even though people like decrease the loss, but it's important that you have a bigger learning rate then along with the bigger batch, because you're gonna decrease your loss much faster. And I think it's also the same thing that the folks at opt at Meta did, because they thought that okay, if you start with a bigger learning rate, the idea is that even if you diverge, you can always decrease it, then actually starting with like a lower learning rate, if that makes sense. Training both VL backbone is important. One key takeaway that I have to say here is that inspired by the paper party, the joint scaled multilingual language model, one thing that they said is that if you scale your vision model, you will get a better performance. So it's very important that you kind of like increase the size of the vision encoder, so you're gonna like get like much better performance out of the box. So that's the key thing that they also taken from that paper, and it seemed to have worked well. Anyway, what are the learnings? What are the things that they have learned as well as the weeks experimenting? So one of the learnings was that a shallow and a wide language models use less spiky training run than a deep and narrow language model. And this was quite interesting. I just left a comment here to say that it will be interesting also to see like the performance from these two type of architecture in a way, right? So not only from stabilizing the training but also the performance. What are the bugs or the mistakes that the team did? One of the things that they did was not having a shared environment, and this will affected them a lot because they um, could not reproduce certain test evaluation because the team used someone else content environment. So the punchline is that library visioning is important when you kind of like working on these large project. Um, so yeah, create a lot of tests, have checks in your code. This is very important. Also, I think it's a very key takeaway is that just having like those assets in your code, making sure that you have right tests, it's gonna help. So yeah, this is Hugging Face. Now let's look at the OPT and how actually this worked. So before we get into OPT, I want to hear your thought. Maybe you can leave a comment. I want to hear your thought on, do you think that some of these challenges are still occurring like recently, given that some of these models that I'm talking about have been pre-trained in 2022? So 2023 was a boom for AI, right? Like there's just so many labs training these large systems at scale, and so many things have been tried. And do you think that we're at the point whereby we don't face these challenges? We just know what works and what does not work. So I'd like to hear your thoughts on that. Anyway, getting into the meta also, they had like numerical instabilities when they were training their OPT. So the challenge was the great norm and activation norm explosion, as we can see from these graph. Also, the loss scale will also diverge. So, what happened before we get into the solutions that did not work is that they had like multiple runs. Like, you can think of like they had the first run, they thought, okay, let's change this and this. They had the second run, and so some of these solutions that did not work, you can think of like they have been attempted across multiple runs. So, weight decay, the team said nope, did not work. Then the team increased the weight decay also to zero point 0.1 from 0.01, but the loss plateaus. Then they started now to think, okay, let's adapt to GPT-3, right? Like they had a successful model, so if we use the hyperparameter, we should be fine, right? But the thing that you must remember is that Meta used, I think, some of the data internally that I don't think that they declosed. I'm not sure about that, but I don't think that they declosed which data they used to kind of like train the OPT. But anyway, what they did was to kind of like set the grade norm, keep it to 1, and they reduced the Atom beta 2 from 0.98 to 0.95. They increased the Atom epsilon from 1 minus 8 to 1 minus 6. Um, they they also did something which is to double the batch size. So they realized that actually using a large batch size did not actually make also a large much difference. Maybe it could have been with the same situation with Hugging Face in that it enabled you to have a large learning rate in the way so that your loss can decrease when you start like right, repeatedly, but in this case, they said that it did not help at all. Hyperparameter tuning after run 10, so I think this was run 11. So what they did was to, okay, maybe let's go back to, instead of going to 0.01, let's go to 0.05. They increased the learning rate. So like I said here, the team thought that starting with a high learning rate is okay, since you can drop it if things start to become unstable. No dropout on embeddings, non-former. So this is a paper. I leave the link here. So essentially, you kind of like add these layer norms on different operations within your layers. So gradients at an early layers are much more large than at the later stage. So adding three normalization operation to each layer does actually help. So that's what they did. They just added like layer norm just to kind of like thinking that this will stabilize. Then we have gradient pre-divide factor. Also, they used it, and they had also a clip of 2.5 2. They also added land positional embedding with seasonal unit, which we'll find out actually they had to change this. It did not help. Then they modify the above parameters to stabilize training. They lowered the learning rate again. They lowered the gradient clipping because it was at 2.5 to 1.5. So they did say that this stabilized grade norm spike training around, but at like 4.5 for 4.5 to 5.5 steps. But going forward, it did not help. But remember that they had something like, I think, 140K steps, if I'm not mistaken, if I can remember. Um, Skipped batches when grade norm is 1.0. That's what they did. So they skip certain batches, and which is, I think, I'm just thinking out loud, which is something that I think the folks at Bloomberg probably should have done, because of the folks at Bloomberg, like they just hit a rock, like they tried different things, and like I just can't get it, like why they could, like why after that 42 day run they couldn't actually start to kind of like see the model stabilize and the loss decrease. So that's what they did. The folks at Meta, they tried to think, okay, maybe we can skip some of the bridge when the grade norm is one. So, but this did not help. Inward non-factor. This was also mentioned by Taz from Hugging Face on the repo, and he advised. We kind of like came up with this solution in which that essentially you kind of like move your non-vector inward. So what happened is that currently, if you try to apply your non-vector after the dot product between A and B, for in this case, for example, uh, the non-factor one have impact because now these things will have like skyrocketed. But what you can do is that you can apply, you can take the square root of the non-factor, then you multiply it with the matrices, then you do the dot product. So you move those non-factors inward. So this improved numerical stabilities. So yeah, it did not work in the meta case, but based on like tasks on GitHub, I think it worked. I think, yeah, I'm not 100% sure, but yeah. Anyway, that's what they did. They removed Gelu and used Relu. So they trained with FP16. So I think this is not mixed precision. I think what they're trying to say here was that so because of when you do mixed precision, you have to make your updates with like the, what is it, FP32. Then they did not do that. Instead, I think they had to like use FP16. Then to avoid the overflow and overflow, they use what we call loss scaling. to preserve small gradient values. So yeah, I left the link here for those who want to kind of like, I think the folks at Craft Core explained this concept much better, the loss scaling concept. But it's very easy. I think you scale your loss, then what you're gonna do is that you're gonna multiply your linen rate by the scale. Yeah, something along those lines. But that's what you do. Anyway, hyperparameter tuning after run 11. So they also faced instabilities. What they did now was to think, okay, we're gonna remove the num factor, the num former setup, which whereby they added like a lot of num layers, then the weight decay, because now it was at 0.05, then they moved it to 0.1. The clipping was now at 0.1. The max learning rate also, the Adam beta 2 was at 0.95. They removed the embedding scalings as well, and also the use Gaussian init for length positional embedding. So they, instead of using this, the seasonal initialization. So yeah, that's what they did. But these things, like the at this point, like the model was still in the training run was still not stable. So solution that worked was linear rate is all you need. So the team just figured it out, right? Like so at the edge, the project was about to run out, but at the edge, like they just figured it out, that actually you need to lower your learning rate. So you can think that, they monitored their metrics very closely. So when they see a little bit of diverge, then they just know that they have to kind of like lower their learning rate more. So this is quite interesting to see that. Then clipping. So they said that it was not a clear cut if it was necessarily helping from 1.0 to 0.3, or it just delayed the spikes. So they were not sure, because like I said, that these people were trying a lot of things. So sometimes they are not necessarily sure what helped. Where to restart? So this is quite important. Is that how to roll back? Let's say you kind of like see that, okay, now you had that spike thing, and now you have to roll back to kind of like start your train again. So they said that actually rolling back quite significantly to avoid these sparks had a major impact. So it's very important that kind of like you take that into consideration. BF16, in this case, they say that it worked very, very well. So it helped the team overcome the numerical instabilities that they face. So this is quite interesting. I have to say thanks to the people that worked on this project and the meta team and everyone, even from Hugging Face. And this is quite really good to learn from these challenges. Anyway, learnings. They said that actually you need to spend time on data as well as data quality. So yeah, like I said, and this is one thing that I thought that having people specifying what kind of data they used on like these projects is very, very important, because now like different labs, they can try to see actually if some of these challenges are pertaining to the data or something else, so yeah, start small and scale. So we can see that the same advice that we got from Hugging Face, I think actually it was Bloomberg, it's also coming up again. So which means that these different labs, they are seeing a very important thing, which is to start small. In the Meta case, what they realized is that they started very huge, then they had like a lot of bugs, and they made like some of the costly mistake. But then that's when like they realized that starting small and scaling, it's very important, because when you start small, you can be able to understand each component, and you can be able to test them initially, and you can see what works and what does not work. So even if you train like 125 million model, like you see actually how your setup works on that range, then you can go ahead and start to scale. So, bugs and mistakes. I have to say that some of the bugs, they just mentioned that we got a bug on tensor parallelism implementation, but they did not get into too much detail, actually. And that's one thing that I was interested in, like distributed training, I think is quite fascinating. So it will be nice to kind of like get into the nitty gritty stuff. But the people that were building this, they were not really integrated in the infrastructure side. Maybe probably that's why they were not like, they did not give information on that. Anyway, the data artifacts, so this is quite important. So they said that they added an extra escape character in the deduplication pipeline. Then the loss was just decreasing, and they were so excited only to find out that it was predicting the escape characters. So yeah, it's very important, folks, that you be careful on your data. So before you can imagine the losses decreasing and find out that it was escape correct. Anyway, weight decay back, they did not mention a lot. What was the back with the weight decay? They just said at run 12 there was a weight decay back. um so yeah, like the tensor parallelism code, like I said, because of they saw that the 125 million failed, and this also shows the importance of starting small. You see, like you train your 125 million model, and you already see these challenges, or before you can like go to something like billion. System issues, CUDA errors. They did not get into the exact CUDA errors that they got. I just mentioned them here, and I know that this might not necessarily help a lot, but maybe it might give some people intuition of some of the challenges that people face. But other than that, guys, I have to say thank you if you have watched all the way to the end. These are the challenges. I'll keep on like updating this repo with new problems and challenges that different labs face, so that you guys get updated all the time. So without wasting your time, thank you very much. I'll see you in the next one.